Hi there, you're in the lab with your mate JJ. Today is QuickStudy cheat sheet review. Today we're going to be reviewing a cheat sheet. My silly job title for today is Electronics Guru. Today I'm the Electronics Guru. And the QuickStudy cheat sheet that we'll be doing is Algebra Part 1. Algebra. So these QuickStudy review papers are 6-page foldouts that are basically like a cheat sheet for particular subjects. We've already done 2 of them. I think we did pre-algebra and we did elementary algebra. And today we're up to algebra part 1. So there is an algebra part 2 as well. Plenty of algebra there. So I've sort of organized them roughly in order of difficulty. So we're just getting started with some basics about algebra. What we'll be doing is popping over to the bench and then having a read through the 6 pages in this compendium, and then we'll wrap up. So let's jump over to the bench and see what's in this thing. All right. So here we are on the bench, and here is our cheat sheet. So I'm just going to read this out and see if we can learn a thing or two about algebra. This is the world's #1 academic outline, Algebra Part 1 from Bar Charts Incorporated. This is QuickStudy Academic. Parts 1 and 2 combined cover principles for basic, intermediate, and college courses. All right, so this is Part 1, set theory. All right, notation. Braces indicate the beginning and end of a set notation. When listed, elements or members must be separated by commas. For example, A equals a set of 4, 8, and 16. Sets are finite, ending, or have a last element unless otherwise indicated. Okay. ... indicates continuation of a pattern. For example, 5, 10, 15, ... 85, 90. Okay. ... at the end indicates the infinite set, that is, a set with no last element. Example, C equals 3, 6, 9, 12, ... They've got a bar. Bar is a symbol which literally means such that. Okay. And then this is a symbol. It means is a member of or is an element of. For example, if A equals 4, 8, 12, then 12 is a member of A because 12 is in set A. Okay. And then there's notation for not a member of or is not an element of. For example, if B equals 2, 4, 6, 8, then 3 is not a member of B because 3 is not in set B. Okay, and then there's a symbol here which means the empty set or the null set, a set containing no elements or members, but which is a subset of all sets, also written as open bracket, close bracket, or braces, open brace, close brace. I'm going to get some coffee. I'll be back. All right, so after the empty set, we have the symbol which means is a subset of, and it's sort of a U rotated to the right like 90 degrees. So it's a sideways U. It means is a subset of, and it may also be written with a line underneath it. And then you have the same symbol with a line through it, means is not a subset of, which also may be written with a line underneath it. So A is a subset of B indicates that every element of set A is also an element of set B. For example, if A equals 3 and 6 and B equals 1, 3, 5, 6, 7, 9, then A is a member of B. Sorry, A is a subset of B. A is a subset of B because the 3 and 6 which are in set A are also in set B. 2 to the power of n is the number of subsets of a set when n equals the number of elements in that set. For example, if A equals 4, 5, 6, then set A has 8 subsets because A has 3 elements and 2 to the power of 3 equals 8. Ah, interesting. Give me a sec. All right, I'm back, and I got myself a notebook here. Today is the 4th of January 2026. Put the date first because I'm an Australian. Day first. Now, what I wanted to do, let's just put this Algebra Part 1, and we're going to say A equals 4, 5, 6. 4, 5, 6. I'll try and do that there. So the subsets are 4, 5, and 6, 4 and 5, 4 and 6, and then 5 and 6, 1, 2, 3, 4, 5, 6, and we've got them one at a time, 4 and 5, 4 and 6, and then there's 4, 5, and 6. But I'm missing something, aren't I? 4 and 5, 4 and 6, 5 and 6, 4, 5 and 6. 1, 2, 3, 4, 5, 6, 7. Do we have to count the empty set? Do we have to count the empty set? I don't know. I don't know. Let's think a bit harder about this. So set of 4, set 5, set 6. Set 4 and 5, 4 and 6, 5 and 6, and 4 and 5 and 6. That's only 7. So they must count the empty set. I'll see if I do some research about that. I'll be back in a sec. All right, I'm back, and I got myself a fresh coffee. So yeah, I just did some research, and it turns out when you're counting the subsets, you count the empty set as well. So there we go. 1 at a time, 2 at a time, 3 at a time, and the empty set. Very good. Okay, operations. Okay, U means union. So this is like the similar symbol, but up. So U for union. A, U, B. A union B indicates the union of set A with set B. Every element of this set is either an element of set A or an element of set B. That is, to form the union of two sets, put all of the elements of both sets together into one set, making sure not to write any element more than once. For example, if A equals 2 and 4 and B equals 4, 8, and 16, then A union B is 2, 4, 8, 16. I've been taught that you can put the duplicates in there, but they don't count twice. So if there was 4, 4, 4, 4 in there, it'd only count once for 4. But of course, there's no point writing it with redundant values. Okay, and now they seem to like this U symbol, don't they? So now they've got the U rotated 180 degrees, and it means intersection. So the A and the intersection of A and B indicates the intersection of set A with set B. Every element of this set is also an element of both set A and set B. That is, to form the intersection of two sets, list only those elements which are found in both of the two sets. For example, if A equals 2 and 4 and B equals 4 and 8 and 16, then the intersection of A and B is 4. I've got a little bit of grit here. See if I can clean that off. All right. So okay. So it seems that there's an overbar. So A with a bar over it indicates the complement of set A. That is, all elements in the universal set which are not in set A. For example, if the universal set is the set of integers and A equals 0, 1, 2, 3, dot, 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 then A minus 1, minus 2, minus 3, minus 4, dot, dot, dot is the complement, A complement R. Okay, so if the universal set is the set of integers, then the complement of A is the set of negative integers. And the intersection of A and its complement is the empty set. The intersection of A and its complement is the empty set. Very good. So properties, we're on to properties. A equals B means all of the elements in set A are also in set B, and all elements in set B are also in set A, although they do not have to be in the same order. Okay, yep. If A equals 5 and 10, and B equals 10 and 5, then A equals B. Okay. And then we've got NA, indicates the number of elements in set A. Okay. So N is the number of distinct elements, say. NA indicates the number of elements in set A. For example, if A equals 2, 4, 6, then NA equals 3. Okay. Tilde means is equivalent to. That is, set A and set B have the same number of elements, although the elements themselves may or may not be the same. Okay. So if A equals 2, 4, 6 and B equals 6, 12, 18, then A is equivalent to B. A is equivalent to B because NA equals 3 and NB equals 3. Oh, isn't that interesting? Okay. So is equivalent to regards the number of elements in the set. And then we've got this intersection again. So the intersection of A and B equals the empty set, indicates disjoint sets which have no elements in common. Okay. Now I should make some notes here. What have we got? We've got U equals subset of is a subset of, and then we've got U equals union, and then we've got this one equals intersection, and that is the empty set. All right, so that's a subset of union intersection. Very good. All right, so we've discussed the properties. Now we look at the sets of numbers. So it says here, the natural or counting numbers, 1, 2, 3, 4, 5, dot, 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 12, sorry, dot, 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 11, 12, dot, dot, dot. So starting at 1 and counting to infinity. Whole numbers starting at 0 and counting to infinity. Integers, including the negative integers, the 0 and the positive integers. The rational numbers, P on Q, where P and Q are integers and Q doesn't equal 0. The set of natural numbers, whole numbers and integers, as well as numbers which can be written as proper or improper fractions, are all subsets of the set of rational numbers. Irrational numbers. X is a real number, but is not a rational number. Okay. The sets of rational numbers and irrational numbers have no elements in common and are, therefore, disjoint sets? Oh, okay. So the rational and the irrational, and then the real numbers, x is the coordinate of a point on a number line. The union of the set of rational numbers with the set of irrational numbers equals the set of real numbers. And then we've got imaginary numbers, AI, where a is a real number and I is the number whose square is -1. I squared equals -1. The sets of real numbers and imaginary numbers have no elements in common. The set of real numbers and imaginary numbers have no elements in common and are therefore disjoint sets. And then there's complex numbers, a plus bi, where a and b are real numbers and I is the number whose square is -1. The set of real numbers and the set of imaginary numbers are both subsets of the set of complex numbers. For example, 4 plus 7i and 3 minus 2i. All right, on we go. Now we're going to look at the properties of real numbers. I'll be back in a tick. All right, so now we're looking at properties of real numbers. Properties of real numbers for any real number, a, b, and c. Property. Okay, so we've got closure. So we've got the property and then the property for addition and the property for multiplication. And the properties are closure, commutative, associative, identity, inverse, and distributive property. Okay. So the closure property for addition means that a plus b is a real number. And the closure property for multiplication, ab is a real number. The commutative property for addition is a plus b equals b plus a. And the commutative property for multiplication is ab equals ba. The associative property for addition is a plus b in brackets plus c equals a plus b plus c in brackets. Similarly, for multiplication, ab in brackets times c is equal to a times b and c in brackets. Okay, so commutative, associative, and the identity. 0 plus a equals a, and a plus 0 equals a. Similarly, the identity property for multiplication, a times 1 equals a, and 1 times a equals a. I don't think they really needed to give us that both ways, did they? Because we've already got the commutative property. Anyway, a little bit of redundancy never killed anyone. So, and the inverse property for addition is a plus negative a equals 0, and negative a plus a equals 0. Whereas for multiplication, the inverse is a times 1 on a equals 1, and 1 on a times a equals 1 if a doesn't equal 0. Yes, right. So that division's not fully sort of reflective, is it? Because you rule out 0 here. You don't have the same problem for addition. And then we've got the thing called the distributive property, which means if you've got a times b plus c, that's equal to ab plus ac. And a times b minus c equals ab minus ac. That's a distributive property. Very good. Okay, properties of equality. For any real numbers a, b, and c. So reflexive. Okay, reflexive just means it equals itself. Properties of equality for any real numbers a, b, and c. Reflexive, a equals a. Symmetric, if a equals b, then b equals a. Transitive, if a equals b and b equals c, then a equals c. Addition property, if a equals b, then A plus C equals B plus C. Multiplication property. If A equals B, then AC equals BC. Multiplication property of 0. A times 0 equals 0, and 0 times A equals 0. Double negative property. Negative negative A equals A. Properties of inequality. For any real numbers for any real numbers A, B, and C, the trichotomy, either A is greater than B, or A equals B, or A is less than B. Transitive. If A is less than B and B is less than C, then A is less than C. Addition property of inequalities. If A is less than B, then A plus C is less than B plus C. And if A is greater than B, then A plus C is greater than B plus C. Multiplication property of inequalities. If C doesn't equal 0 and C is greater than 0, then A is greater than B. If C is not 0 and C is greater than 0 and A is greater than B, then AC is greater than BC. Also, if A is less than B, then AC is less than BC. If C is not equal to 0 and C is less than 0 and A is greater than B, then AC is less than BC. Also, if A is less than B, then AC is greater than BC. That doesn't make sense, does it? If A is less than B, how can AC be greater than BC? Is that wrong? If C is not 0, and C is negative, there we go. C is negative. So, yeah, right. So if C is negative and A is smaller, then that's correct. Okay, fine, good. So this number is negative. It'll be greater than this number, which will be more negative. Very good. Operations of real numbers. Absolute value. The absolute value of x is x if x is 0 or a positive number. The absolute value of x, where x equals negative x, if x is a negative number, that is the distance, which is always positive, of a number from 0 on the number line is the absolute value of that number. I don't know why it says absolute value of x equals negative x. Oh, I see. If x is a negative number, then you get a double negative and it becomes positive. Wow, okay. Yep, got it, fine. So it's the distance on the number line between 0 and the point, or the value of that number. For example, the absolute value of -4 equals minus 4 equals 4. Absolute value of 29 is 29. Absolute value of 0 is 0. Absolute value of -43 equals 43. Addition. If the signs of the numbers are the same, if the signs of the numbers are the same, add the absolute values of the numbers. The sign of the answer is the same as the sign of the original two numbers. For example, -11 and -5 is -16, and 16 plus 10 is 26. If the signs of the numbers are different, subtract the absolute values of the numbers. The answer has the same sign as the number with the largest absolute value. For example, -16 plus 4 equals -12, and -3 plus 10 equals 7. All right. Subtraction. A minus B equals A plus negative B. Subtraction is changed to addition of the opposite number. That is, change the sign of the second number and follow the rules of addition. Never change the sign of the first number since it is the number in back of the subtraction sign which is being subtracted. 14 minus 6 not equals minus 16. Sorry, 14 minus 6 doesn't equal minus 14 plus minus 6. For example, 15 minus 42 equals 15 plus negative 42 equals negative 27. And negative 24 minus 5 equals negative 24 plus negative 5 equals negative 29. And negative 13 minus 45 equals negative 13 plus 45 equals 32. And then again, negative 62 minus negative 20 equals negative 62 plus 20 equals negative 42. Multiplication. The product of two numbers which have the same sign is positive. The product of two numbers which have the same sign is positive. For example, 55 times 3 is 165, and minus 30 times minus 4 equals 120, and minus 5 times minus 12 equals 60. The product of two numbers which have different signs is negative, no matter which number is larger. For example, minus 3 times 70 equals minus 210, and 21 times negative 40 equals minus 840, and 50 times minus 3 equals negative 150. Division, where the divisors are not equal to 0. The divisor is, of course, the number on the bottom of the ratio or the fraction. The quotient of two numbers which have the same sign is positive. For example, minus 14 divided by minus 7 equals 2, and 44 divided by 11 equals 4. Minus 4 divided by minus 8 equals 0.5. The quotient of two numbers which have different signs is negative, no matter which number is larger. For example, minus 24 divided by 6 equals minus 4, and 40 divided by minus 8 equals negative 5, and minus 14 divided by 56 equals negative 0.25. And then we've got double negative. Negative A equals A. That is, the negative sign changes the sign of the contents of the parentheses. For example, minus 4 is 4, and minus 17 is 17. All right, on we go. So there we got through our first page, and there's a lot more in store for us, isn't there? All right, so now we're up to algebraic terms. Combining like terms. Adding or subtracting. A plus A equals 2A. When adding or subtracting terms, they must have exactly the same variables and exponents, although not necessarily in the same order. These are called the terms. The coefficients, numbers in the front, may or may not be the same. The rule is combine, which is add or subtract. Add or subtract only the coefficient of like terms and never change the exponents during addition or subtraction. For example, 4xy cubed and negative 7y cubed x these are like terms and may be combined in this manner. 4xy cubed plus 7y cubed x equals minus 3xy cubed. Notice only the coefficients were combined and no exponent changed. Minus 15a squared bc and 3bc a to the power of 4 are not like terms because the exponents of a are not the same in both terms. so they may not be combined. Okay. Multiplying. Product rule for exponents. A to the power of m times a to the power of n equals a to the power of m plus n. Any terms may be multiplied, not just like terms. The coefficient and the variables are multiplied, which means the exponents also change. The rule is multiply the coefficients and multiply the variables. This means that you have to add the exponents of the same variable. For example, 4a squared c times minus 12a cubed b squared c equals minus 48 a to the power of 5, b to the power of 2, and c to the power of 2. Notice that 4 times negative 12 becomes negative 48. A squared times a cubed becomes a to the 5th. C times c becomes c squared. And the b cubed was written down. Right. Sorry, I don't understand that. Oh, I see. Sorry, of course. So the b squared was in the second term. It wasn't in the first term, so it's just come straight through. The reason I was confused is I was looking at that, and the b squared in both of them, but those are the wrong two numbers to compare. It's these two numbers here, so that makes perfect sense. The b squared just comes through because there's no b in the first term. All right, distributive property for polynomials. All right, we've got type 1, a outside of c plus d equals AC plus AD. For example, 4x cubed times 2xy plus y squared equals 8x to the 4y plus 4x cubed times y squared. Yeah, okay. So that's type 1. And then you've got type 2. I see. Okay. So in type 2, you've got a plus b times c plus d, which you can rewrite as type 1. So that's a times cd plus b times cd. And then you can, what do you call that, collecting like terms or expanding? I'm not sure. Anyway, you can then expand that as AC plus AD plus BC plus BD. For example, 2x plus y outside of 3x minus 5y equals 2x out of 3x minus 5y plus y outside of 3x minus 5y. And then do we call it collecting like terms? Just add everything up and we get 6x squared minus 10xy plus 3xy minus 5y squared. And then that simplifies a bit. So you got 6x squared minus 7xy minus 5y squared. And then we've got type 3. Oh, wow, okay. So type 3 is going to go into the polynomial here. What do you call the polynomial that's got 3 parts in it? I'm not sure. I'll be back in a sec, just going to get a drink. All right, so we're up to type 3, which is a plus b times c squared plus cd plus d squared equals a outside of c squared plus cd plus d squared plus b outside of c squared plus cd plus d squared. And then you expand those and you get ac squared plus acd plus ad squared plus bc squared plus bcd plus bd squared. Okay. Okay, and then there's an example here. 5x plus 3y outside of x squared minus 6xy plus 4y squared equals 5x outside of x squared minus 6xy plus 4y squared plus 3y outside of x squared minus 6xy plus 4y squared equals 5x cubed minus 30x squared y plus 20xy squared plus 3x squared y minus 18xy squared plus 12y cubed equals 5x cubed minus 27x squared y plus 2xy squared plus 12y cubed. Okay, and then we've got the FOIL method for products of binomials. FOIL, the FOIL, it's the first, outer, inner, last. Is that right? Method for products of binomials. This is a popular method for multiplying two terms by two terms only. FOIL means first times first, outer times outer, inner times inner, and last times last. For example, 2x plus 3y outside of x plus 5y would be multiplied by multiplying the first term times the first term, which is 2x times x, which equals 2x squared. Then the outer terms is 2x times 5y, which is 10xy. And then the inner terms, 3y times x equals 3xy, and then the last term times the last term, which is 3y times 5y equals 15y squared. Then combining the like terms of 10xy and 3xy gives 13xy, with the final answer equaling 2x squared plus 13xy plus 15y squared. All right. Now we've got a note here about some special products. So the type 1 special products is a plus b squared, which is the same as a plus b times a plus b, which equals a squared plus 2ab plus b squared. Very good. And then we do type 2 is a minus b squared, which is a minus b times a minus b equals a squared minus 2ab plus b squared. And we've got type 3. Which is a plus b times a minus b, which is a squared plus 0ab minus b squared equals a squared minus b squared. Great. All right, and now we're on to exponent rules. Rule 1, a to the power of m to the power of n is a to the power of m times n, and a to the power of m to the power of n means the parentheses contents are multiplied m times, and when you multiply, you add exponents. For example, negative 2m to the power of 4n squared all to the power of 3 equals minus 2m to the 4n squared times minus 2m to the 4n squared times, okay, so they've just expanded the power of 3, and then they've so you multiply and then you add. Okay, so multiplying negative 2 gives you negative 8. Multiplying m to the 4th and m to the 4th and m to the 4th gives you n to the 12, and n squared plus n times n squared equals n to the 6. Notice the parentheses were multiplied 3 times, and then the rules of regular multiplication of terms were used. Shortcut rule. When raising a term to a power, just multiply exponents. For example, minus 2m to the power of 4n squared all to the power of 3 equals minus 2 to the power of 3, m to the power of 12, n to the power of 6. Notice that the exponents of the minus 2, m4, and n squared were all multiplied by the exponent 3, and that the answer was the same as the example above. Right. Caution. Negative a to the m not equals negative a to the m. These two expressions are different. Are they? For example, okay. So they give us an example here, minus 4yz squared doesn't equal minus 4yz squared because minus 4yz squared equals yeah, okay, sure. So that equals that times that, which equals that. Well, minus 4yz squared. Oh, I see. Yeah, of course. Okay. Okay. So I hope you followed all of that. Basically, they're just saying that if you put it all in brackets, that's different to just the z squared. Yeah. So the exponent 2 applies only to the z. Yeah. So in this case, the exponent's only on the z. And I guess on this case, the exponent is on the a, and then you subtract it last. Interesting. Okay, now we've got rule 2, ab to the power of m. Just give me a sec, I'll be back. All right, well, I just wanted to get myself a second opinion on this this caution here where minus a to the m doesn't equal minus a to the m when it's in brackets. So ordinarily you do the exponentiation before you do the unary minus. So there you go. That unary minus happens at the same precedence as addition and subtraction, which is lower precedence than exponentiation. So there you go. So those two expressions are different. I hadn't appreciated that, I don't think. I have to remember that. All right. So there's an example here. It says negative 4yz squared doesn't equal negative 4yz in brackets squared because minus 4yz in brackets squared equals minus 4yz times minus 4yz, which equals 16y squared z squared. Well, minus 4yz means minus 4 times y times z squared. Right. And the exponent 2 applies only to the z in this situation. Fair enough. Now we've got rule 2, ab to the power of m equals a to the m times b to the m. For example, 6x cubed y to the power of 2 equals 6 squared plus x to the power of 6 times y to the power of 2, which equals 36 x to the 6th and y squared, but 6x cubed plus y all squared equals 6x cubed plus y outside of 6x cubed plus y equals 36x to the 6 plus 12x to the 3y plus y squared. Because there is more than one term in the parentheses, the distributive property for polynomials must be used in this situation. All right. Rule 3. So a on b to the power of m equals a to the power of m divided by b to the power of m when b doesn't equal 0. For example, so they give you an example here. So these this fraction all squared equals the square of the top times the square of the bottom divided by the square of the bottom. Rule 4, 0 power a to the 0 equals 1 when a doesn't equal 0. Oh, I didn't know that. So when a is 0, 0 to the 0 doesn't equal 1. Oh, I'm going to go read a bit more about that. Hang on. All right, so I just confirmed that and it's correct. So 0 to the power of 0 is undefined. You could argue that it's 1 or you could argue that it's 0. There's no consistent value, so it's just undefined. 0 to the power of 0, undefined. Then the quotient rule, a to the m divided by a to the n equals a m minus n. Any terms may be divided, not just like terms. The coefficients and the variables are divided, which means the exponents also change. Rule. The rule is divide coefficients and divide variables. This means you have to subtract the exponents of matching variables. For example, minus 20 times x to the 5th y squared z divided by 5x squared z equals minus 4 x cubed y cubed, and the z's cancel. Notice that minus 20 divided by 5 becomes minus 4. X to the 5th divided by x squared becomes x cubed. And z divided by z become 1, and therefore did not have to be written because 1 times minus 4 xy x cubed y squared equals minus 4x squared y squared. Yeah. Negative exponent. A to the power of negative n equals 1 on a to the n, where a not equals 0. For example, 2 to the power of negative 1 equals 1/2. 4z to the power of negative 3 times y squared divided by minus 3ab to the power of negative 1 equals 4 y squared Oh, I see. So they take the negative parts and just put them in the bottom. So you've got 4y squared I'm gonna have to think carefully about this. I'll be back. All right, I'm back, and I understand this now. The thing that tricked me was that in the answer, the b to the power of 1 ends up on the top here, and that's because it's divided by negative 1. So those cancel. So essentially the negative means it has to go to the other side of the fraction. So I knew that the z to the power of minus 3 would send the z to the bottom, as it does here. But what I've just learned is that the b to the power of minus 1, when it's in the divisor, just flips over to put it in the dividend. So so I understand this expression now. Very good. Notice that the 4 and the negative 3 both stayed where they were because they both had an invisible exponent of positive 1. the y remained in the numerator and the a remained in the denominator because their exponents were both positive numbers. The z moved down and then the b moved up because their exponents were negative numbers. Very good. So I could have just read the instructions before I figured it out, but anyway, all's well that ends well. On we go. So the steps for solving a first degree equation with one variable. First, eliminate any fractions by using the multiplication property of equality. For example, 1/2 outside of 3a plus 5 equals 2/3 of 7a minus 5 plus 9 would be multiplied on both sides of the equal sign by the lowest common denominator of 1/2 and 2/3, which is 6. The result would be 3 times 3a plus 5 equals 4 times 7a minus 5 plus 54. Notice that only the half and the 2/3, notice that only the half, the 2/3, and the 9 were multiplied by 6 and not the contents of the parentheses. The parentheses will be handled in the next step, which is distribution. Second, simplify the left side of the equation as much as possible by using the order of operations, the distributive property, and combining like terms. Do the same to the right side of the equation. For example, use distribution first. So 3 outside of 2k minus 5 plus 6k minus 2 equals 5. Minus 2 outside of k plus 3 would become 6k minus 15 plus 6k minus 2 equals 5 minus 2k minus 6. And then combine like terms to get 12k minus 17 equals minus 1 equals minus 2k. Okay. Third, apply the addition property of equality to simplify and organize all terms containing the variable on one side of the equation and all terms which we do not combine the variable on the other side. For example, 12k minus 17 equals minus 1 2k would become 2k plus 12k minus 17 plus 17 equals minus 1 plus 17 minus 2k plus 2k, and then combining like terms you get 14k equals 16. Then fourth, apply the multiplication property of equality to make the coefficient of the variable 1. For example, 14k equals 16 would be multiplied on both sides by 1 on 14 or divided by 14 to get a 1 in front of the k, so the equation would become 1k equals 16 divided by 14, or simply k equals 1 1/7 or 1.143. Fifth, check the answer by substituting it for the variable in the original equation to see if it works. Note, some equations have exactly one solution. They are conditional equations. For example, 2k equals 18. Some equations work for all real numbers. They are identities. For example, 2k equals 2k. Okay. Okay. And some equations have no solutions. They are inconsistent equations. So 2k plus 3 equals 2k plus 7. Right, yeah, okay. That's an inconsistent equation. There you go. Steps for solving a first degree inequality with one variable. Okay, so we're doing an inequality now, an inequality with one variable. Addition property of inequalities. For all real numbers a, b, and c, the inequalities A is less than B and A plus C is less than B plus C are equivalent. That is, any terms may be added to both sides of an inequality and the inequality remains a true statement. This also applies to A is greater than B and A plus C is greater than B plus C. Multiplication property of inequalities. For all real numbers A, B, and C with C not equal 0 and C greater than 0, the inequalities A greater than B and AC is greater than BC are equivalent, and the inequalities A is less than B and AC is less than BC are equivalent. That is, when C is a positive number, the inequality symbols stay the same as they were before the multiplication. For example, if 8 is greater than 3, then multiplying by 2 would make 16 greater than 6, which is a true statement. For all real numbers A, B, C with C not equal 0 and C less than 0, the inequalities A greater than B and AC less than BC are equivalent, and the inequalities A is less than B and AC is greater than BC are equivalent. That is, when C is a negative number, the inequality symbols must be reversed from the way they were before the multiplication for the inequality to remain a true statement. For example, if 8 is greater than 3, then multiplying by minus 2 would make minus 16 greater than minus 6, which is false unless the inequality symbol is reversed to make it true. For example, minus 16 is less than minus 6. Steps for solving. First, simplify the left side of the inequality in the same manner as an equation, applying the order of operations, the distributive property, and combining like terms. Simplify the right side in the same manner. Second, apply the addition property of inequality to get all terms which have the variable on one side of the inequality symbol and all terms which do not have the variable on the other side of the symbol. Third, apply the multiplication property of inequality to get the coefficient of the variable to be a 1. Remember to reverse the inequality symbol when multiplying or dividing by a negative number. This is not done when multiplying or dividing by a positive number. Fourth, check the solution by substituting some numerical values of the variable in the original inequality. All right, that's 2 down and 4 to go. All right, so now we're up to the order of operations. I already did some research on that, didn't I? I'm going to take a quick break. All right, so now we're reading about the order of operations. So first, simplify any enclosed symbols. Parentheses, brackets, and braces. Parentheses, brackets, and braces. If present. 1. I can just get some more light on that. Yeah. 1. Work the enclosure symbols from the innermost and work outward. Work separately above and below any fraction bars, since the entire top of a fraction bar is treated as though it has its own individual enclosure symbols around it, and the entire bottom is treated the same way. Second, simplify any exponents and roots. Working from left to right, note that the square root symbol is used only to indicate the positive root, except that the square root of 0 is 0. Okay. Third, do any multiplication and division. Do any multiplication and division in the order in which they occur, working from left to right. Note, if division comes before multiplication, then it is done first. If multiplication comes first, then it is done first. Fourth, do any addition and subtraction in the order in which they occur, working from left to right. Note, if subtraction comes before addition in the problem, then it is done first. If addition comes first, then it is done first. Okay, factoring. Some algebraic polynomials cannot be factored. The following are methods of handling those which can be factored. When the factoring process is complete, the answer can always be checked by multiplying the factors out to see if the original problem is the result. That will happen if the factorization is a correct one. A polynomial is factored when it is written as a product of polynomials with integer coefficients and all of the factors are prime. The order of the factors does not matter. First step, GCF. Factor out the greatest common factor, if there is one. The greatest common factor is the largest number which will divide evenly into every coefficient together with the lowest exponent of each variable common to all terms. For example, 15a cubed c cubed plus 25a squared c to the power of 4 d cubed minus 10a squared plus c cubed d has a greatest common factor of 5a squared c cubed. Okay, because 5 divides evenly into 15, 25, and 10. The lowest degree of a in all three terms is 2. The lowest degree of c is 3. The greatest common factor is 5a squared c cubed. If the factorization is 5a squared c cubed outside of 3a plus 5cd squared minus 2d. Okay, the second step is to categorize and factor. Identify the problem as belonging to one of the following categories. Okay, there's a big table of categories here. Identify the problem as belonging in one of the following categories. Be sure to place the terms in the correct order first. Highest degree term to the lowest degree term. For example, minus 2a cubed plus a to the power of 4 plus 1 equals a to the power of 4 minus 2a to the power of 3 plus 1. All right. Category. Okay, so there's 4 categories. We've got trinomials with 3 terms, binomials with 2 terms, perfect cubes with 4 terms, and grouping. All right. So when the category is trinomials with 3 terms, the form of the problem is ax squared plus bx plus c, where a doesn't equal 0. So there we've got a perfect square as an example, x squared plus 2cx plus c squared. Form of factors. If a equals 1, x plus h times x plus k, where h times k equals c and h plus k equals b, h and k may be either positive or negative numbers. If a doesn't equal 1, then mx plus h times nx plus k, where m and n equal a and h times k equals c, then h times n plus m times k equals b. M, h, n, and k may be either positive or negative numbers. Trial and error methods may be needed. See special factoring hints. That's the next section. X plus c times x plus c equals x plus c squared, where c may be either a positive or negative number. Okay. Now we're going to do the two-term binomials. Binomials. So we've got the difference of two squares, which is a squared x squared minus b squared y squared. A squared x squared plus b squared y squared. The difference of two squares, sum of two squares, sum of two cubes, difference of two cubes. So we've got ax plus by times ax minus by cannot be factored. Ax plus by outside of a squared x squared minus abxy plus b squared y squared. Okay, I'm gonna need to take a break. I'll be back. All right, so I understand this a bit better now. These different cases line up across the columns here, so that was a bit confusing for me. Anyway, we did the first trinomial, and the second trinomial we did was a perfect square, and then we're doing binomials over here, and the first one's called the difference of two squares, and it just factors as this, and then the sum of two squares is prime, can't be factored because there's no common bits on either side. Fair enough. And then there's this one, the sum of two cubes. And with that, you can pull out the factor ax plus by, and then have this other trinomial here. And then we've got the difference of two cubes. That's okay, so it refers to the special factoring hints, which are over here. So we'll be looking at those in a second. So then the category of perfect cubes, which we include four terms. Sorry, give me a second again. All right, so in category 3 here, we've got perfect cubes, which are four terms. Gee whiz. So this monster, a cubed x cubed plus 3a squared bx squared plus 3ab squared x plus b cubed, factors as ax plus b cubed, which is ax plus b, and ax plus b. And then you can do the same cubed with the negative b. I'm not sure what you call that part. It's is it a coefficient of x to the power of 1 or x to the power of 0? Maybe. Anyway, that expands as this. So okay. And then grouping. So the fourth category, okay, so you can pull the A out there and the B out there. Okay, and then you can rearrange it. So 2 minus 2 grouping. Okay, and then 3 minus 1 grouping. X squared plus 2cx plus y squared minus y. Okay, so you get these factors here. And y cubed minus x squared minus 2cx minus x squared. So c squared. That's 1 to 3 grouping. Yeah, right. There you go. Now we're on to special factoring hints. Trinomials. Okay, trinomials. That just means three terms where the coefficient of the highest degree term is not 1. Oh, that's interesting. Where the highest degree term is not 1. I thought it had to be not 0. But it's not. It says not 1. The first term in each set of parentheses must multiply to equal the first term, the highest degree of the problem. The second term in each set of parentheses must multiply to equal the last term in the problem. The middle term must be checked on a trial and error basis using outer times outer plus inner times inner as ax squared plus bx plus c equals mx plus h times nx plus k, where mx times nx equals ax squared, h times k equals c, and mx times k plus h times nx equals bx. For example, to factor 3x squared plus 17x minus 6, all of the following are possible correct factorizations. Okay, so we've got 3x plus 3 out of x minus 2, and we've got 3x plus 2 times x minus 3, and we've got 3x plus 6 outside of x minus 1, 3x plus 1 outside of 6 minus x. Okay, wow, 1, 2, 3, 4. 4 different factorizations. However, the only set which results in a 17x for the middle term when applying outer times outer plus inner times inner is the last one, 3x plus 1 equals 6x minus 6. It results in minus 17x and plus 17x is needed, so both signs must be changed to get the correct middle term. Therefore, the correct factorization is 3x minus 1 outside of x plus 6. Ah, okay. Gee, that's all a bit tricky, isn't it? Binomials. The sum or difference of two cubes. This type of problem, a cubed, x cubed, plus or minus b cubed, y cubed, requires the memorization of the following procedure. The factors are two sets of parentheses with 2 terms in the first set and 3 terms in the second. To find the 2 terms in the first set of parentheses, take the cube root of both of the terms in the problem and join them by the same middle sign found in the problem. The 3 terms in the second set of parentheses are generated from the 2 terms in the first set of parentheses. The first term in this, sorry, did I get that wrong? The first term in the second set of parentheses is the square of the first term in the first set of parentheses. The last term in the second set is the square of the last term in the first set. The middle term of the second set of parentheses is found by multiplying the first term and the second term from the first set of parentheses together by changing the sign. Thus, a cubed x cubed plus or minus b cubed y cubed equals ax plus or minus by outside of a squared x squared minus or plus ab xy plus b squared y squared. For example, to factor 27x cubed minus 8, find the first set of parentheses to be 3x minus 2, because the cube root of 27x cubed is 3x and the cube root of 8 is 2. And then find the 3 terms in the second set of parentheses by squaring 3x to get 9x squared. Square the last term to get term minus 2 to get plus 4. And to find the middle term, multiply 3x times minus 2 and change the sign to get plus 6x. Therefore, the final factorization of 27x cubed minus 8 is 3x minus 2 times 9x squared plus 6x plus 4. Okay, and then we've got some notes on perfect cubes, which have 4 terms. Perfect cubes, such as a cubed x cubed plus or minus 3a squared bx squared plus 3ab squared x plus or minus b cubed, factor into 3 sets of parentheses, each containing exactly the same 2 terms. Therefore, the final factorization is written as one set of parentheses to the third power, thus a perfect cubed. So you got ax plus or minus b all cubed equals a cubed x cubed plus or minus 3a squared bx squared plus 3ab squared x plus or minus b cubed. For example, to factor 27x cubed minus 54x squared plus 36x minus 8, it must first be observed that the problem is in correct order and that it is a perfect cube. Then the answer is simply to the cubed roots of the first term and the last term placed in a set of parentheses to the third power, so that the answer to this example is 3x minus 2 all cubed. Notice to student. This guide is the first of 2 guides outlining the major topics taught in algebra courses. It is a durable and inexpensive study tool and can be repeatedly referred to during and well beyond your college years. Due to its condensed format, however, use it as an algebra guide and not as a replacement for assigned coursework. All rights reserved, blah, blah, blah. Okay. So, what do we got next? Rational expressions. Definition. The quotient of 2 polynomials where the denominator cannot equal 0 is a rational expression. Gonna take a break. Okay, well, we're halfway through. Now we're doing rational expressions. Definition. The quotient of 2 polynomials where the denominator cannot equal 0 is a rational expression. Oh, that's interesting. For example, x plus 4 divided by x minus 3, where x doesn't equal 3, since 3 would make the denominator x minus 3 equal to 0. Okay. Basics. Domain. The set of all real numbers which can be used to replace a variable. The domain for the rational expression x plus 5 times x minus 2 divided by x plus 1 times 4 minus x is the x where x is a real number and x doesn't equal -1 or it doesn't equal 4. That is, x can be any real number except -1 or 4, because -1 makes x plus 1 equal 0, and 4 makes 4 minus x equal to 0. Therefore, the denominator would equal 0, which it must not. 2. Notice the numbers which make numerator equal to 0. Notice that numbers which make the numerator equal to 0, -5 and 2, are members of the domain, since fractions may have 0 in the numerator but not in the denominator. Right. Rule 1. If x divided by y is a rational expression, then x divided by y equals x times a divided by y times a, where a doesn't equal 0. That is, You may multiply a rational expression or fraction by any non-zero value as long as you multiply both the numerator and the denominator by the same value. The equivalent to multiplying by 1, since a divided by a equals 1. Okay, for example, x divided by y times 1 equals x divided by 1, x divided by y times a divided by a equals x times a divided by y times a. Note, 1 is equal to any fraction which has the same numerator and denominator, except for 0. Rule 2. If x on a divided by if xa divided by ya is a rational expression, then xa divided by ya equals x divided by y, where a doesn't equal 0. That is, you may write a rational expression in lowest term because xa divided by ya equals x divided by y times a divided by a equals x divided by y times 1 equals x divided by y, since a divided by a equals 1, as long as a not equals 0. Lowest terms. Rational expressions are in lowest terms when they have no common factors other than 1. Step 1. Completely factor both numerator and denominator. Step 2. Divide both the numerator and the denominator by the greatest common factor or by the common factors until no common factors remain. For example, x squared plus 8x plus 15 divided by x squared plus 3x minus 10 equals x plus 5 times x plus 3 divided by x plus 5 times x minus 2. And what cancels? X plus 5 cancels. So we get x plus 3 divided by x minus 2. Because the common factor of x plus 5 was divided into the numerator and the denominator, since x plus 5 divided by x plus 5 equals 1. Note, only factors can be divided into both numerators and denominators, never terms. Only factors can be divided into both numerators and denominators, never terms. Right. Operations. Addition. Denominators must be the same. Rule 1. If a divided by b and c divided by b are rational expressions and b doesn't equal 0, then a on b plus c on b equals a plus c on b. If denominators are already the same, simply add numerators and write this sum over the common denominator. Rule 2. If a divided by b and c divided by d are rational expressions and b not equals 0 and d not equals 0, then a on b plus c on d equals a times d on b times d plus c b on bd equals ad plus cb divided by bd. If numerators are not the same, they must be made the same before numerators can be added. Okay, and this is the case where there wasn't a common factor. You just multiply them out. You can actually just do this even if there is a common factor, but yeah, fair enough. Addition steps. If the denominators are the same, then add the numerators and write the answer over the common denominator. Write the final answer in lowest terms, making sure to follow directions for finding the lowest terms as indicated above. Okay, and there's an example here. X plus 2 divided by x minus 6 plus x minus 1 divided by x minus 6 equals 2x plus 1 on x minus 6. And that was just a straight up addition because the denominators were the same. If the denominators are not the same, Then find the least common denominator. Change all of the rational expressions so they have the same common denominator. Okay, add the numerators, write the sum over the common denominator, and then write the final answer in lowest terms. So we've got x plus 3 divided by x plus 5 plus x plus 1 divided by x minus 1. So we multiply out and we get x plus 3 times x minus 1 divided by x plus 5 times x minus 1. And the same on this side. X plus 1 times x plus 5 and x minus 1 times x plus 5, and then we simplify it to this. Note, if the denominators of a degree greater than 1, if the denominators are of a degree greater than 1, try to factor all denominators first, so the least common denominator will be the product of all different factors from each denominator. Subtraction. Denominators must be the same, so it's the same as addition in that regard. But rule 1, if a divided by b and c divided by b are rational expressions and b doesn't equal 0, then a on b minus c on b equals a on b plus minus c on b equals a minus c on b. If the denominators are same, be sure to change all signs of the terms in the numerator and rational expression, which is behind, to the right of, subtraction sign. Then add numerators and write the result over the common denominator. For example, x minus 3 on x plus 1 minus x plus 7 on x plus 1 equals x minus 3 minus x plus 7, which equals minus 10 on x plus 1. All right, and then we've got rule number 2. If a, b, and c, d are rational expressions, and b not equal 0 and d not equal 0, then a on b minus c on d equals ad on bd minus cb on bd equals ad minus cb on bd. If numerators are not the same, they must be made the same before numerators can be subtracted. Be sure to change signs of all terms in numerator and rational expressions which follows subtraction sign after rational expressions have been made to have a common denominator. Combine numerator terms and write the result over common denominator. B. Note, when denominators of rational expressions are additive inverses. Hang on a sec, I'll be back. All right, there's a note here. When denominators of rational expressions are additive inverses, that is, they have opposite signs, then signs of all terms in denominator of expression behind subtraction sign should be changed. This will make denominators the same, and terms of numerators can be combined as they are. Subtraction of rational expressions is changed to addition of opposite of either numerator most of the time or denominator, most useful when denominators are additive inverses, but never both. Subtraction steps. If the denominators are the same, then change signs of all terms in numerator of a rational expression which follows any subtraction sign, then add the numerators. Write the answer to this addition over the common denominator, and write the final answer in lowest terms, making sure to follow directions for finding the lowest terms as indicated above. For example, x plus 2 divided by x minus 6 minus x minus 1 divided by x minus 6 equals x plus 2 plus minus x plus 1 equals 3 on x minus 6. If the denominators are not the same, then find the least common denominator, change all of the rational expressions so they have the same common denominator, multiply factors in the numerator if there are any, change the signs of all of the terms in the numerator of any rational expressions which are behind subtraction signs, add the numerators, write the sum over the common denominator, and write the final answer in lowest terms. For example, x plus 3 divided by x plus 5 minus x plus 1 divided by x minus 1 equals x plus 3 times x minus 1 on x plus 5 times x minus 1 minus x plus 1 times x plus 5 and x minus 1 times x plus 5 equals minus 4x minus 8 on x squared plus 4x minus 5. Note, if denominators are of a degree greater than 1, try to factor all denominators first, so the least common denominator will be the product of all different factors from each denominator. And then we've got multiplication. The denominators do not have to be the same. Okay, so when we're multiplying, the denominators don't have to be the same. So if A, B, C, and D are real numbers and B and D are non-zero, then A on B times C on D equals AC on BD. Top times top and bottom times bottom. Multiplication steps. Completely factor all numerators and denominators. Write the problem as one big fraction with all numerators written as factors, multiplication indicated on top, and all denominators written as factors, multiplication indicated on bottom. Divide both numerator and denominator by the common factors, that is, write it in lowest terms. Multiply the remaining factors in the numerator together and write the result as the final numerator. Multiply the factors in the denominator together and write the result as the final denominator. So here we've got x plus 3 on x squared plus 2x plus 1 times x squared minus 2x minus 3 on x squared minus 9. So we factor those bits and pieces and we cancel the bits and pieces and we're left with 1 on x plus 1. Neat. All right, now up to page 5. 555. All right, so okay, now we're going to continue with division. This is rational expressions regarding division. So the reciprocal of a rational expression xy is y on x. Sorry, that's x divided by y is y divided by x, because x divided by y times y divided by x equals 1. The reciprocal may be found by inverting the expression. For example, the reciprocal of x minus 3 divided by x plus 7 is x plus 7 divided by x minus 3, where x not equals 3. Rule: if A, B, C, D are real numbers, A, B, C, and D are non-zero numbers, then A on B plus C on D equals AB times DC equals AD on BC. So that's a negative, that's a divising. So basically you take the inverse of CD and it becomes DC, and then you just straight through multiply them. Division steps: reciprocate, flip. Okay, reciprocate, there you go. So flip the rational expression found behind the division sign, immediately to the right of the division sign. Multiply resulting rational expressions, making sure to follow steps for multiplication as listed above. Okay, now here's this monster. Look at this. X squared minus 2x minus 15 divided by x squared minus 10x plus 25 divided by x plus 2 over x minus 5. And we reciprocate, and then we just straight out multiply. So we reciprocate over here, and that just flips, and then the numerators and denominators would then be factored, written in lowest terms, and yield a final answer of x plus 3 and x plus 2. Oh yeah. Complex fractions. An understanding of the operations section of rational expressions is required to work complex fractions. Definition: A rational expression having a fraction in the numerator and denominator, or both, is a complex fraction. A rational expression having a fraction in the numerator or denominator, or both, is a complex fraction. Okay? 2 available methods. Simplify the numerator. Combine rational expressions found only on top of the complex fraction, and denominator. Combine rational expressions found only on the bottom of the complex fraction. Then divide numerator by denominator, that is, multiply numerator by the reciprocal of the denominator, or multiply the complex fraction, both in numerator and denominator, by least common denominator of all individual fractions which appear anywhere in the complex fraction. This will eliminate the fractions on top and bottom of the complex fraction and result in one simple rational expression. Follow steps listed for simplifying rational expressions. Synthetic division. Definition. A process used to divide a polynomial by a binomial in the form of x plus h, where h is an integer. Steps. Write the polynomial in descending order from highest to lowest power of variables, for example, 3x cubed minus 6x plus 2. Write all the coefficients of dividend under long division symbol. Oh dear. Write all coefficients of dividend under long division symbol, making sure to write zeros, which are coefficients of powers of variables which are not in the polynomial. For example, writing coefficients of polynomial in the example above, write 3, 0, minus 6, plus 2. Okay? Because 0 is needed for the x squared, which isn't there. Okay? And then write the binomial in descending order. For example, x minus 2. Okay? Then write the additive inverse of constant term of binomial in front of long division sign as divisor. For example, the additive inverse of the minus 2 in the binomial x minus 2 is simply plus 2. That is, change the sign of this term. Bring up first number in dividend. So it will become first number in quotient. Multiply the number just placed by quotient by divisor. 2. Add result of multiplication to next number in dividend. Result of this addition is next number coefficient in quotient. So write it over next coefficient in dividend. Repeat step 6 until all coefficients in dividend have been used. Last number in the quotient is the number of a remainder, which is written as a fraction with the binomial as the denominator. For example, 2 into 3, 0 minus 6, 2 results in a quotient of 3, 6, 6 with a remainder of 14. Therefore, 3x cubed minus 6x plus 2 divided by x plus 2 equals 3x squared plus 6x plus 6 plus 14 on x minus 2. I didn't really understand that long division bit there. I'm going to have to do some practice problems, I think, to get that right in my head. But yeah, you do this long division here, and you get a bunch of new coefficients. First exponent in answer, the quotient, is 1 less than the highest power of dividend because division was by a variable to first degree. Yeah, right. Okay. Roots and radicals. Basics. Definition. The real number b is the nth root of a if b to the power of n equals a. I'm going to take a break, get some coffee. I'm just going to make a note about synthetic division. This is this long division thing that we just looked at previously. I'm going to have to do some practice with this because I don't really get it yet. So I've made a note to follow up on that. So I know we started, but let's start again. Let's have a look here. We've got roots and radicals. So the basics, the definition. The real number b is the nth root of a if b to the power of n equals a. Radical notation. If n doesn't equal 0, then a to the power of 1 on n equals the nth root of a, and the nth root of a equals a to the power of 1 on n. The symbol is the radical, or the root symbol, and the a is the radicand. Okay, so the symbol is the radical, and the root symbol, the root symbol and the radical, same thing. And the a is the radicand. The n is the index or order. Index or order. Special note, equation a squared equals 4 has two solutions, 2 and negative 2. However, the radical to square root of a represents only the non-negative square root of a. Okay. Definition of square root. For any real number a, the square root of a squared equals the absolute value of a. That is the non-negative numerical value of a only. For example, the square root of 4 equals 2 by definition of the square root. Okay. Rules. For any real numbers m and n, with m divided by n in lowest terms and n not equal 0, a to the power of m on n equals a to the power of m to the power of 1 on n equals the nth root of a to the m, or a to the m on n equals a to the power of 1 on n to the power of m, which is the nth root of a to the power of m, so they're equivalent. For any real number m and n, with m and n for any real numbers m and n, with m and m, with m on m in lowest terms, and n not equal 0, a to the power of negative n, m on n equals 1 divided by a to the power of m on n. Okay. For any non-zero real number n, a to the power of n to the power of 1 on n equals a to the power of 1 or a. Or a to the power of 1 on n to the power of n equals a to the power of 1 equals a. Either way. Great. For real numbers a and b, and natural number n, the nth root of a times the nth root of b equals the nth root of a times b, or the nth root of a times b equals the nth root of a times the nth root of b. That is, as long as the radical expressions have the same index, n, they may be multiplied together and written as one radical expression of a product, or they may be separated and written as the product of two or more radical expressions. The radicands do not have to be the same for multiplication. For real numbers a and b, and natural number n, the nth root of a divided by the nth root of b equals the nth root of a divided by b, or the nth root of a on b equals the nth root of a divided by the nth root of b. That is, as long as the radical expressions have the same index, they may be written as one quotient under one radical symbol, or they may be separated and written as one radical expression over another radical expression. The radicands do not have to be the same for division. Terms containing radical expressions. Terms containing radical expressions cannot be combined unless they are like or similar terms and the radical expressions which they contain are the same. The indices and radicands must be the same for addition and subtraction. For example, 3x times the square root of negative 2 plus 5x times the square root of 2 equals 8x times the square root of 2. But 3y square root of 5 plus 7y square root of 3 cannot be combined because the radical expressions they contain are not the same. The terms 7m and the square root of 2 and 8m and the cube root of 2 cannot be combined because the indices, plural of index, are not the same. Right. Simplifying radical expressions. When the radical expression contains one term and no fractions, simplifying radical expressions. When the radical expression contains one term and no fractions, for example, the square root of 12m squared, then take the greatest root of the coefficient. For example, root 32, use root 16 times root 2, not root 4 times 8, because the square root of 8 is not in simplest form. Okay. Take the greatest root of each variable in the term. Remember, the nth root of a to the n equals a. That is, the power of the variable is divided by the index. This is accomplished by first noting if the power of the variable in the radicand is less than the index. If it is, the radical expression is in its simplest form. If the power of the variable is not less than the index, divide the power by the index. The quotient is the new power of the variable to be written outside of the radical symbol. The remainder is the new power of the variable still written inside the radical symbol. For example, the cube root of a to the 7th equals a squared a squared times the cube root of a, or the cube root of a 8 times a times b to the 5th equals 2b outside of the cube root of ab squared. When the radical expression contains more than one term and no fractions, for example, x squared, the square root of x squared plus 6x plus 9, then factor if possible and take the root of the factors. Never take the root of individual terms out of a radicand. Right. For example, x squared plus 4 not equals x plus 2, but x squared plus 4x plus 4 equals the square root of x plus 2 squared equals x plus 2, because the root of the factors x plus 2 squared was taken to get x plus 2 as the answer. If the radicand is not factorable, then the radical expression cannot be simplified because you cannot take the root of the terms of a radicand. When the radical expression contains fractions, if the fraction is part of one radicand under the radical symbol, for example, the square root of x on 3, then simplify the radicand as much as possible to take the radicand one rational expression, to make the radicand one rational expression so it can be separated into the root and the numerator over the root of the denominator. Simplify the radical expression in the numerator, simplify the radical expression in the denominator. All right, now we're up to page 6, and we're just going to continue with what we were looking at, which is the roots and radicals continued. So this is B. Never leave a radical expression in the denominator. It is not considered completely simplified until the fraction is in lowest terms. Rationalize the expression to remove the radical expression from the denominator as follows. Step 1. Multiply the numerator and the denominator by the radical expression needed to eliminate the radical expression from the denominator. A radical expression in the numerator is acceptable. For example, 5x times root 2 on 7 times root 3. The square root of 3 must be multiplied by square root of 3 on the square root of 3, so the denominator becomes 21 with no radical symbols in it. The numerator becomes 5x times the square root of 6. Step 2, write the answer in lowest terms. If the fraction contains monomial radical expressions, for example, x on the square root of 5, then A, if the radical expression is in the numerator only, simplify it and write the fraction in lowest terms. If the radical expression is in the denominator only, rationalize the fraction so no radical symbols remain there. Simplify the resulting fraction to lowest terms. And C, if the radical expressions are in both the numerator and denominator, either simplify each separately, rationalize the denominator and write the answer in lowest terms, or make the indices on all radical symbols the same, put the numerator and the denominator under one common radical symbol, write in lowest terms, separate again into radical expressions in the numerator and a radical expression in the denominator, rationalize the denominator and write the answer in lowest terms. 3. If the radical expressions are part of polynomials in a rational expression, for example, x plus root 2 on 3x plus root 5, then if the radical expressions are not in the denominator, then simplify the fraction and write the answer in lowest terms. If the radical expressions are in the denominator, rationalize it by multiplying the numerator and the denominator by the conjugate of the denominator. Conjugates are expressions with the middle sign changed. For example, the conjugate of 3x plus 5 root 2 is 3x minus 5 root 2 because when they are multiplied, the radical symbol is eliminated. Rational expressions in equations. Definition: equations containing rational expressions are algebraic fractions. Okay. Steps: determine the least common denominator for all rational expressions in the equation. Use the multiplication property of equality to multiply all terms on both sides of the equality sign by the common denominator and thereby eliminate all algebraic fractions. Solve the resulting equation using appropriate steps depending on the degree of the equation which resulted from the following step 2. 4. Check answers because numerical values which cause denominators of rational expressions in original equation to be equal to 0 are extraneous solutions, not true solutions of the original equation. All right. Radical operations. Addition and subtraction. Only radical expressions which have the same index and the same radicand may be added. Multiplication and division. Monomials may be multiplied when the indices are the same, even though the radicands are not. For example, 3x root 5 times 2 root 7 equals 6x times the square root of 35. And binomials may be multiplied using any method for multiplying regular binomial expressions if indices are the same. Use FOIL, which is first outer inner last from page 2. For example, 9m plus 2 root 5 times 3m minus 5 root 7 equals 27m squared minus 45m times the square root of 7 plus 6m times the square root of 5 minus 10 times the square root of 35. Other polynomials are multiplied using the distributive property for multiplication if the indices are the same. Division may be simplification of radical expressions or multiplication by the reciprocal of the divisor. Rationalize the answer so it is in lowest terms without a radical expression in the denominator. Then we've got radical expressions in equations. Rule: both sides of an expression may be raised to the same power. Caution: since both entire sides must be raised to the same power, place each side in a separate set of parentheses first. Steps: if the equation has only one radical expression, for example, the square root of 3x plus 5 equals x, then isolate the radical expression on one side of the equal sign. Raise both sides of the equation to the same power as the index. Solve the resulting equation and check the solutions in the original equation because extraneous solutions are possible. For example, the square root of 3x plus 5 equals x becomes the square root of 3x equals x minus 5. Then squaring both sides gives 3x equals x squared minus 10x plus 25, because when the entire right side, which is the binomial x minus 5, is squared, x minus 5 squared, the result is x squared minus 10x plus 25. This is now a second degree equation. The steps for solving a quadratic equation should now be followed. With equations containing two radical expressions, for example, this minus the square root of x plus the square root of 2x equals 4, change the radical expressions to have the same index. Separate the radical expressions, placing one on each side of the equal sign. Raise both sides of the equation to the same power as the index. Repeat steps B and C above until all radical expressions are eliminated. Solve the resulting equation and check the solutions. If the equation has more than two radicals, change the radical expression to the same index. Separate as many radical expressions as possible on different sides of the equal sign. Raise both sides of the equation to the power of the index. Repeat steps B and C above until all radical expressions are eliminated. Solve the resulting equation and check the solutions. And then we've got quadratic equations. Definition: second degree equations in one variable which can be written in the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers and a not equals 0. The property, if a and b are real numbers and a times b equals 0, then either a equals 0 or b equals 0 or both equal 0. At least one of the numbers has to be equal to 0. Steps: set the equation equal to 0, combine like terms, write in descending order, factor. If factoring is not possible, then go to the next step. Set each factor equal to 0, see above. If a product is equal to 0, at least one of the factors must be 0. Solve each resulting equation and check the solutions. Use the quadratic formula if factoring is not possible. The quadratic formula is x equals minus b plus or minus the square root of b squared minus 4ac over 2a. A, B, and C come from the second degree equation, which is to be solved. After the second degree equation has been set to equal 0, A is the coefficient, the number in front of the second degree term. B is the coefficient, the number in front of the first degree term. If no first degree term is present, then B is 0. And C is the constant term, no variable showing. So note ax squared plus bx plus c equals 0. Substitute the numerical values for a, b, and c into the quadratic formula. Simplify completely. Write the two answers, one with plus in front of the radical expression and one with minus in front of the radical expression in the formula. Complete any additional simplification to get the answers in the required form. And then complex numbers. They're going to sneak in some complex numbers. The definition: the set of all numbers a plus bi, where a and b are real numbers and I squared equals -1. That is, I is the number whose square equals -1, or I equals the square root of -1. Note I squared equals -1 will be used in multiplication and division. The complex number 3 plus 2i not equals 3 minus 2i, because the numbers must be identical to be equal. Operations: addition and subtraction. Combine complex numbers as though I was a variable. For example, 4 plus 5i plus 7 minus 3i equals 11 plus 2i. And minus 3 plus 7i minus 5 minus 8i equals minus 8 plus 15i. The sum or difference of complex numbers is another complex number. Even the number 21 is a complex number in the form a plus bi, where a is 21 and b is 0. Multiplication and division. Multiply complex numbers using the methods for multiplying two binomials. Remember that I squared equals -1, so the answer is not complete until I squared has been replaced with -1 and simplified. For example, -3 plus 5i times 1 minus I equals -3 plus 3i plus 5i minus 5i squared equals -3 plus 3i plus 5i minus 5 times -1. And I'm not sure what's missing there, something, and then that just simplifies to 2 plus 8i. Divide the complex numbers by rationalizing the denominator. The answer is complete when there is no radical expression or I in the denominator, and the answer is in simplest form. For example, the conjugate of the complex number -3 plus 12i is -3 minus 12i. And that's it. That's the end of our cheat sheet. So I would certainly encourage you to get your own copy. It looks like a pretty good, handy cheat sheet. So you can spend an hour or two and just refresh your memory of algebra. When we do our next QuickStudy cheat sheet, we'll be doing Algebra Part 2. So stand by for that. Should be coming out next Sunday, assuming everything goes according to plan. So I'll throw you the farewell cam. We'll wrap up. And that's a wrap. So that was Algebra Part 1. We'll be doing Algebra Part 2 next week. This was all mostly revision for me. I vaguely remember algebra as it was presented here in Part 1. I think the thing that I really didn't understand was synthetic division. So I'll probably need to do some revision around that. Apart from that, everything else felt pretty familiar to me, so that's good. I expect as we get right into the weeds with these, that we're going to actually hit the limit of my experience. But I felt pretty confident that I knew most of what was in here, although I am a bit rusty and I could do with a textbook full of practice questions for just drilling the mathematics. Anyway, that's the end of this video. So I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.